geometric quantization of argument shift on the universal enveloping algebra of GLN. Gusha, you're welcome.
Okay, just a moment. Так меня слышно в зуме? Я просто повесил этот микрофон, как Ларингов.
Гоша, если не будет слышно, кто-нибудь скажет.
Okay.
Но я думаю, что слышно.
Okay. So I go on. So this this talk is a continuation of few talks which I made here in the last year and probably the year before that, and it deals with the following question. Suppose you have a Lie algebra G. And then, as you know, as everybody knows, its dual space is equipped with a Poisson structure. So it is Poisson manifold, where the Poisson bracket of the coordinates can be identified with the Lie brackets of the corresponding elements in the Lie algebra. This is an important example of Poisson structures, which is studied in many, which emerges in many different situations, in many cases, and I think in the last like 100 years, people have introduced few examples of commutative subalgebras in the algebra of function on this Poisson manifold. So I'll restrict my attention to the space of polynomial functions on G star. So first of all, one can ask about the Casimir functions here. And one knows that they are precisely the functions, the polynomials on G, which are invariant with respect to the joint action of the group G, of the group which is associated with the Lie algebra G, small g. For example, when G is equal to GLN, which will be my, well, which will be the example which I will study today. This space is well known. And it is equal to the free algebra over the ground field K, either real or complex numbers, doesn't matter, generated by n polynomials C1, Cn, and one can choose these polynomials in many different ways. For instance, Ci can be taken to be the coefficient, the ith coefficients of the universal characteristic polynomial of matrix. So here L is the matrix of generators of the group of the Lie algebra GLN. E1 is the unit matrix, and we have the polynomial expansion of this formula something like -1 to the power I, lambda I, C, probably n minus I will be more appropriate, of L. So these are polynomials in terms of the matrix elements of this universal generators matrix, right? Any questions? Okay, but this is pretty well known. There are also other possible choices of generators of this center. For instance, you can take trace in the usual sense of the matrix L to the power k, and take k to go, let k go from 1 to n. This is also a set of generators of this center of this Casimir functions algebra. But however, of course, central elements, even though they are very important, are not the major subject of the study. And it is much more important to have other commutative subalgebras. There exist many different examples of commutative subalgebras, and many of them come from the following observation. Suppose you have Poisson manifold M, which is equipped with two, not with one, but with two Poisson structures, 0 and 1. And we assume that these Poisson structures are compatible in the sense that their linear combination is a Poisson bracket for all lambdas. Real or complex doesn't matter. Then the following is true. Let Z sub lambda be the center. So this is a subspace or subalgebra in the space of functions on M. And be the algebra of Casimir functions with respect to this lambda bracket. Right. Then for every two elements, A in Z lambda 1 and B in Z lambda 2, the Poisson bracket respect to any element in this pencil of Poisson structures vanishes identically. The proof is very easy. I just use this opportunity to give this proof. Actually, of course, it's been known for ages. So the proof is something like this. Proof. Consider the bracket A and B sub lambda. It is a function. It is an element of the following linear space. It should be function on M and lambda some other function on M. So in some sense, it is kind of linear expression in terms of lambda. Linear in terms of lambda. So this doesn't depend on lambda, and this doesn't depend on lambda. Right? But if lambda is equal to lambda 1, it vanishes. And if lambda is equal to lambda 2, it also vanishes. So we have a linear function which finishes in two distinct points. Well, of course, if lambda 1 is equal to lambda 2, they commute. There is no problem. They are from the same center. But if from different, we have a linear function which vanishes in 2 points. So it means that it should be identically 0. There exist many examples of such structures. I'll give you a couple of examples. One is the subject of future investigation, which is still quite mysterious. And the other one is the famous Mishenko-Fomenko argument shift. So this mysterious part, even though it's quite simple, is the case of so-called A bracket. So suppose you have G equal to GLN again. Choose a fixed matrix A and consider the following bracket on the space of matrices. So we take x and y and consider x a y minus y a x. Well, the usual bracket is just x comma y equal to x y minus y x. So it, so to say, corresponds to a equal to 1. So these two brackets give rise to a pencil of Poisson structures on SGLN. It's not very hard to describe this. The corresponding commutative subalgebra can be described pretty easily. It depends on, in the sense,
by A.
Yeah, but actually, I would say if you fix A and then multiply it by, it's not one pencil, but a series of pencils, I would say.
And Jacobi identity is simple.
Yeah, it's just straightforward computation. Pretty simple, yeah. Takes, well, 5 to 10 minutes, depending on your computational prowess. So this is so this commutative subalgebra. Well, I invite everybody to consider this subalgebra, corresponding commutative subalgebra in SGLN. Well, I haven't seen it studied in any serious way, although it's quite a natural example. Very natural, very simple. Not the only one, by the way, not the only one exotic pencil which you can consider here. But the standard pencil, due to Mishenko-Fomenko and Fomenko, is the following. Consider consider the bracket of xi and xj in the form Cijk xk. So it's generic for any Lie algebra. Yeah. Arbitrary G. Choose any constants A1, AN. N is the dimension of G. And consider the Poisson bracket xi, xj sub A b equals Cij, ak. So this is Poisson bracket just because on the right we have constants. So it's always Poisson when we have constants on the right. The fact that this Poisson bracket is compatible with this is actually easy to compute by direct computation. Direct computation. Easy to check. In fact, you can consider the following shift on Lie algebra. Every element x in G goes to x plus A, where A is the corresponding element here, right? I'd rather say not in G, in G star, probably better to put it like this. So x1, xj are there just coordinates in G star. So just
Yes, but what is x?
It's an element in G star. You can change its coordinates by adding the constants to its coordinates.
So this A is not this.
It's just this. It's just this.
Just
this. Yeah, just this. So you have function f. You can now consider function f of x plus A. Of course, this is isomorphism of the algebra as G isomorphic to SG. You can use this isomorphism to pull the Poisson structure from right to left or from left to right. It depends on your choice. So one can see, so if you put lambda here, that the Poisson structure you pull using this shift will be precisely a pencil of the Poisson structures corresponding to the first and the second elements here. Okay. So that's the classical story. And I'm going to consider this case, Mishenko-Fomenko algebras, in a particular situation where G is equal to GLN. And I'll be dealing with the following question, which was first asked by Winberg in 1990. Is it possible to raise the commutative subalgebra corresponding to Mishenko-Fomenko shift operator, shift pencil, to the universal enveloping algebra, UG. When I say raise, I mean that you have the Poincare-Verhofstadt the isomorphism of the graded algebra associated with the filtration on UG and SG, right? So now you have a Poisson commutative subalgebra here, and you can ask whether, so this is linearly isomorphic to the UG itself, right? That's Poincare-Verhofstadt theorem. You can now ask if you can,
like vector spaces.
yeah, so this is vector space, of course, vector space. You can actually do this isomorphism in such a way that the Poisson bracket will be represented by commutator here.
This isomorphism is not unique, is it?
It's not unique, right? Definitely is not
So
unique.
the thing is, you have all of these possible isomorphisms that
There are different
are
isomorphisms.
really
If there were,
amongst them, you can try to find one which is preserved.
yeah. Actually, it's not even the case. You're not even looking for the whole isomorphism from left to right, from whole linear part of them. You're only interested in this subspace. You're looking for the linear terms here, so that A will be sent to commuting elements, right? Yeah. If there were an isomorphism, some fixed isomorphisms from left to right, it wouldn't be interesting. You just use this isomorphism and you're done. But you can actually modify this isomorphism by adding terms of lower degrees. Because top degree terms are fixed by this isomorphism, actually, top degrees. But lower degrees are totally free. Are free for you to choose. So this question was answered by there were several people working on this subject, and there were several answers, all positive. So first of all, in about 1995, I think, Aishansky and Nazarov developed the theory of twisted Yangians and showed that one can actually raise this algebra, Mishenko-Fomenko algebra, from SG to a commutative subalgebra in UG. They did it not for all Lie algebras, but only for classical series. GLN, A series, B series, C, and D. And I think, as far as I can remember, I don't know if they were able to do this for exotic series E and F and G.
So they considered only semi-simple.
Yeah. Because I think Yangians, when you construct Yangians, there is this the assumption of semi-simplicity is embedded there. And actually, everything's done to this day has been done only for semi-simple case.
Is it because the abstractions lie in some cohomologies? Or?
Abstractions lie in some cohomology, right? And it's hard to compute anything there. Number two, there was a construction in 2001 by Tarasov who dealt with GLN case, and he showed, in fact, that the simplest symmetrization method which you can use to raise elements from here to here works for GLN case. You take the generators of the form Ci of L, coefficients of the universal determinant, right, of the universal characteristic polynomial, shift them by this shifting element A, small a, right? Decompose it, well, put T here to get the decomposition, the parameter of decomposition. Decompose it in powers of T, you get T K C I comma K L A sum over K, and then these coefficients, if you just symmetrize them, you get commutative subalgebra here in universal envelope.
Way around.
Sorry?
The symmetrized ones are on the right.
Yeah, you symmetrize them, but if you
What I'm saying is, you symmetrize, you get something in SG. If you symmetrize.
but no, they are already in SG. They are from the beginning in SG.
So why do you want to symmetrize?
Because I want to raise them from SG to universal enveloping. Because
they're already symmetrized if they're in SG.
but you know, if you want to raise something from SG, in SG, when you have a monomial in SG, you don't have a fixed prescribed order of product of the factors in your product, right? Mm-hmm. So how do you choose the order in which?
No, you do, because it's symmetrized.
But
it's in SG.
But you know, if you have element XY in SG,
then you also have YX.
How do yeah? But yeah. So if you regard this SG as just a polynomial algebra, you just have this, which is of course equal to YX.
In SG.
Yeah, in SG. So if you regard SG as just polynomial algebra, then you need to go from SG to universal enveloping. But if you regard SG as a subspace, subalgebra in tensor algebra, then you're right. You just identify it and just make its projection onto UG.
Well, I'm just a bit confused because I don't understand why you need to symmetrize something in UG. Things in
No. I mean,
As far as
I need a map from SG to UG. I need a map from SG to UG. How do I obtain it? How do I get a map from SG to UG? I have an element as in SG. Well, of course, it should be linear, so it's sufficient to consider monomial. And this monomial looks like xy, xi, x1, and so on, x some d. D is degree. So how do you raise it to universal enveloping? Well, if you just write x1, xd, then you are in trouble because this monomial is here is in fact equal to xd, x1, xd minus 1. And this is not equal in universal enveloping algebra. Right? So you need to either fix the order of the factors here, and that will give you some map, actually. You can do it. But that map is not very good because this map will not commute with the action of the group, of the Lie group. Or you can just use a symmetrization map. You just take elements here and send it to the sum x sigma 1, x sigma d. Sigma is an element.
surely what it was to begin with. It was in SG. Surely it was like that already at the very beginning.
It depends on how you regard SG. If you regard SG as an element, is a subspace in TG, in tensor algebra, then you're right. Every element is of this form there. You're fixed. But if you regard it as a polynomial algebra, and it's different. Yeah. It's just the point of view. It's not something very specific. It depends on your point of view, nothing else. It's just, you're right, you can actually spare this part. Then there was another important paper by Lenya Rybnikov in 2006, I believe. Who also did this for all semi-simple algebras. At least for those of them where the Feygin-Fraenkel center exists. He actually, what he did was
That is something in the universal
Feygin-Fraenkel center.
Is it in the?
No. It's something much harder. It's you take G. You first change it to algebra of currents, I believe. Oh, the loop algebra, right? This algebra has the canonical extension, yeah, central extension. You take the universal enveloping algebra of this central extension, and then you fix k equal to a certain number to the critical value. And what you get will be a very large non-commutative universal algebra.
Take the Cartan subalgebra.
What?
How are you supposed to take the Cartan subalgebra?
I'm not sure about this.
Something like that.
I'm not sure. I'm not sure about this.
Sorry, for any field or for complex?
Let's fix complex numbers. I don't want to go far. For complex numbers, you can find a very large commutative subalgebra there called the Feygin-Fraenkel center. And then what Lenya did, he showed that there exists a map from this Feygin-Fraenkel center from the whole Kac-Moody algebra to UG, which will send the Feygin-Fraenkel center to commutative subalgebra, and the generators of this commutative subalgebra will come from the generators of Feygin-Fraenkel center. So you can actually show that they will cover the Mishenko-Fomenko algebra. So that was the idea of Leonid Rybnikov. So, as you see, these algebras exist, but what I'm interested in finding the operator, the shifting operator on universal enveloping algebra, which would generate the algebra, this commutative subalgebra here.
Exactly, Rybnikov's example.
Actually, all these examples give you the same algebra. That's an important property. All these examples, all constructions give the same algebra. That's an important property, which I am going to use. So the question which I'm going to address is the following. Does they exist, whether they exist, or probably better to say find an operator on universal enveloping algebra. Let's stick our attention to GLN case, such that an operator D sub A, such that created applications of this operator to the element in the center of UGLN generate, well, give you the Mishenko-Fomenko, quantum Mishenko-Fomenko algebra. So quantum Mishenko-Fomenko algebra is any one of these three examples here. They are all the same.
What is P?
P is just
Power.
yeah, power.
Yeah.
So
And what does hetero mean?
het means that it's quantum. It's not
What is it?
yeah, it's
So
universal relevant.
You have to take all P's, right?
Yeah.
So you mean the set of this thing
Yeah.
with P going.
Yeah. So let me explain what I mean by giving the classical example. So in case of SG, what operator do you have?
Just adding A.
Sorry?
Just adding A.
Yeah, adding A, but you can actually write it as a differentiation, because when you take F and go to F x plus A, it will be equal to F of x plus D dA F x and so on. Yeah, yeah, and 1 over k factorial dk dA F of x. And yeah, probably, yeah, you need to put T here, right? And let me see if I'm not mistaken. I probably need to T to TA. You have T, A, K. So this operator, these coefficients, these are constants. So you can actually forget about them. These are constants. But these coefficients, they are commutative elements in SG. So you take F in the center of SG and Casimir functions. Take this, take the F squared, the A squared, and so on, and that will give you the commutative algebra.
You mean the Poisson center?
So this is a Poisson center, yeah, Poisson center, of course. So in particular, it means that if you take any element F and G in the Poisson center of SG, take any, let me note this operator as D sub A, take any dA to the power P of F, dA to the power Q of G, and you get 0 as a result. So I need to find an operator here. Maybe I use het to distinguish it from that example, such that when you apply it iteratively to elements in the center, in the usual center, algebraic center, you get 0. Identically. So in this sense, I mean, this construction, I mean, of course, the existence of these algebras has been known for some time, and their structures has been studied actively by various people. First of all, by Alexander Molev and his co-authors. But nobody has ever thought about this kind of operator. And why I tried to look for this operator, because I tried to bring these constructions within the framework of deformation quantization, precisely to speak about some cohomology abstractions for this problem of phrasing an algebra into universal enveloping algebra. All these constructions, they're purely algebraic. Nobody speaks about deformation here. There is no trace of of classical situation in these constructions. So they are either very combinatorial, like here, or or use some pure algebraic stuff like Yangians or Feigen-Frankel, and that's so that they are not very geometric at all. So I was trying to get some geometric idea about this. Sorry, someone is calling me. Oh, it's my mom. Алло, мам. Я сейчас на семинаре, извини, не могу говорить. Алло. Алло. Алло, мама. Наверное, все. Извините. Sorry. So, I've been searching for this operator for quite some time. Sorry? The existence of this operator, actually, we proved this theorem that we conjectured that some operator would verify this condition quite some time, well, two years ago. And we managed to prove that it is so in GLN case just last year, last summer. After this, we tried to extend this, well, with the help of Professor Molev, to extend it to other Lie algebras. It turned out that in that case, the naive way to extend it fails. So the situation with other Lie algebras, non-GLN, is still not clear. Although I'm sure that there exists a correct way to do this. One need to modify this construction.
Well, because you haven't told us it, but I can imagine it's some complicated form.
Yeah.
But I'm just wondering, I mean, probably. But anyway, the thing is that you're in the classical case, you were able to get these D's. You were represented just by translation.
Yeah.
So I'm just wondering, it may have, of course, I have to wait and see, but I wonder if there might be some way to present this in some nice closed way and similar.
Yeah, in GLN, that's what I'm going to show you, to give you. Yeah, I can describe you these shifting.
Closed, like the analog X plus A.
Yeah, not as in this way, but as an analog of d over dA.
Yes, that's what I'm saying. Is that it would be nice if you could get the analog of X plus A.
Oh.
That would involve some. I mean,
I think I have an idea how to do this, and that's actually more appropriate.
That would be nice.
That would probably solve the problem for other Lie groups.
Yes.
But let me begin with something I can do in GLN case. So I'm going to generalize this operator to an operator on 'U' GLN. And to this end, I'll consider so-called quasi-derivations. They were first introduced by Gurevich, Pyatov, and Safonov in 2012, although I'm sure they appeared under various guises long time before that. I'm almost sure they were known to at least Greenfield. So here is the definition. The definition heavily uses the explicit set of generators of UGLN. So I'll denote the generators by EIJ. Ij vary from 1 to n. And I also assume that the following commutation relation holds. EIJ, when you commute with EPQ, gives you delta IQ EJP minus vice versa. Just to set the notation. There are different ways to write down this relation, but I'll give this notation. So now quasi-derivations are the set of operators D hat Ij. Probably better to use it like this. Yeah, okay, like Ij. From UGLN to UGLN, which verify the following conditions. First, Dij hat of 1 is equal to 0. We need this because the Leibniz rule will not hold, but will hold something which is similar to it, which looks like it, but which I cannot use it to prove this condition. So we need to postulate it. 2, Dij hat applied to EPQ is equal to delta IQ delta JP. Just this. And final, the last but not the least, is the relation called the deformed Leibniz rule, twisted Leibniz rule. When you have Dij hat and apply it to the product of f and g, it will equal to D hat Ij f times g plus f D hat Ij g plus sum over k d k I f, I believe it should be like this, d k j g.
It's not so symmetric.
It's quite symmetric, in fact. I forgot about the hat.
You don't have to put plus the other way around.
It's not just the product of in the usual sense, but you can actually show that if you take the operator theta.
Sorry, FG is equal to GF, right?
No. F and G are in UGLN, so they don't commute. It's operator on UGLN, as you see. So F and G are from UGLN.
Yes.
So if you take, one can show that if you take theta equal to, so theta is a map from UGLN to matrices with coefficients in UGLN given by the formula theta of f is equal to f times 1 plus the matrix of partial quasi-derivations, and it will be a homomorphism of algebras.
So this is a way to embed
It's not an embedding effect.
Developing algebra to matrices.
Over UGLN, right? But it's somewhat, let's say, the tautology.
Any generalizations to other cases or is it specific?
Plenty of them, but plenty actually.
Plenty?
Yeah, plenty. You can actually show that this is equal, in fact, to the following map. You take UGLN, you can multiply it.
That's very surprising.
It's very simple. And you take the representation, the tautological representation. Yeah, no, on the left representation, and you get it here. And this will be precisely theta. Just this, very simple. Now you can, here is a very simple way to generalize. You take various representations here, change representations.
I'm sorry.
And get very
X from U to matrices.
Yeah.
And here you
Oh, sorry, forgot. So the row is a representation, so it ends in matrices. It's just a slip of hand. Just a slip of hand. Now we can actually modify it by choosing other representations. You see?
It's strange because here I see no, in the diagram, I see no quasi-derivations.
They are matrix elements of theta.
Here they are.
They're matrix elements of theta. Matrix coefficients of theta, if you subtract the diagonal term, are just quasi-derivations, nothing else. There is another way to generalize it, another way to interpret it, geometric. Another way to interpret it, geometric. So you take SGLN and you use desymmetrization, that the inverse of that symmetrization map, which I had on that blackboard, on that part of the blackboard, identify it with UGLN. Then you'd use this theta map here, end up in matrices, UGLN, and then you symmetrize it, desymmetrize again. So you symmetrize theta and desymmetrize, you end up in matrices with coefficients as SGLN. Now, if you want to get this, you need to do the following thing. Take the matrix of usual partial derivations and take exponent of this matrix. And that's precisely what we have here.
I don't understand.
Oh, it's just
no. I don't understand formally. So we see how to understand it in the long arm. We see no I and J. It does not depend on
here.
No, in the long path.
In the long path,
yeah.
We do.
Where?
Hidden here. When you end up in matrices, that means you have indices.
Ah, yes, we see it here.
Here, hidden here. There is a third way to interpret it, which I actually believe is the most appropriate way to look onto this construction. Let me give you this third description of the quasi-derivations. You consider the group GLN, which you embed into matrices with complex or real coefficients, doesn't matter. Then you consider the differential operators of GLN, on this group, and you can actually show that it is equal to the tensor product. So with polynomial coefficients, polynomial with respect to the standard matrices, standard coordinates in matrices.
I do not understand. What do you mean by differential operators of GLN? Well, as a
So you actually can forget about GLN for a while. Just think about matrices.
yes.
And you can speak about polynomial differential operators on matrices. А. Я думал, что...
So we consider it as a vector space.
Yeah.
Okay.
You can actually regard it as a vector space.
Yeah.
Consider the differential operators. But the importance why I insist on considering them as differential operators on GLN is because here you have the action of GLN group. And then you can actually write it down as a space of functions, of polynomial functions on GLN. Polynomial with respect to this coefficient, this matrices. Tensor with left invariant differential operators. And the simplest way to show this is just to use explicit expressions for left invariant differential operators. You can just write them as polynomial expressions of the form xij d over dxjk, sum over j. Yeah, I'm not mistaken, if I'm not mistaken, something like that. So these are just the vector fields left invariant, then you use these vector fields to generate everything here, and the remaining part will come from the function. So this is how you obtain this isomorphism. It's just some polynomial structure. Now we can actually use now this identification that left invariant differential operators, GLN, differential operators, left invariant differential operators, is nothing else but the universal enveloping algebra of UGLN, right? And then you can do the following trick. Take a function f on SGLN, any polynomial function here. You get it as a differential operator of degree 0 on GLN. Take any element phi in UGLN. We get it as differential operator here. Then you can do the following trick. Take the commutator of f and phi, decompose it as certain elements, psi alpha tensor g alpha, where these are functions.
How can you consider
Of two differential operators. This is differential operator of degree 0, and this is differential operators of some.
you consider it 0 order.
Yeah, nothing else. And you decompose it as this formal sum. And then you can do the following thing. You can actually take this, for instance, and it takes its values at certain point A. So if f is equal to the trace, then this will be precisely equal to the operator which I seek. dA of f of phi is equal to sum aij d hat ij of phi. So this is the shift operator. And here is an interpretation of this operator in terms of differential operators.
That's not the end of it.
That's not the end. And the idea is to prove that this when you iterate it, apply it to central elements, you get commuting elements all the time.
But if that is your operator, isn't it true that is it just the shift operator?
Well, it depends on how you define the shift. Here is a definition. Here is a way you interpret it in terms of algebra, of Lie group. Yeah.
Yes, just the trace. And if you consider traces of powers, what will happen?
It's a good question. I believe that's precisely the way you need to act to generalize it to arbitrary Lie groups. You need to do the same construction here. Take an element which is a character of some representation. Commute it with phi, take the value at certain point, and then what you get will be precisely the generalization. Because when you take the powers, the tensor powers, you get more or less these P's and Q's.
So this is only for special phi that is defined like this.
Sorry?
This formula is this one that you wrote to the
No, that's for arbitrary.
This one here is only true for special phi.
No. It's true for. So this is the definition of the shift operator for any phi in universal enveloping algebra.
So then why is it not the case that the exponential of this dA is just a shift?
But how do you shift elements in universal enveloping algebra? How do you shift them? You can actually do this, but I don't know how to explain this in an appropriate way. I just don't know, but it is actually a shift. And here is the interpretation of the shift in terms of.
If it acts on the lowest term, it'll just shift x to x plus a.
Yeah.
I guess if it's on the next one, it has to act on x tends to y as x plus a tends to y plus a.
I don't know. I think it would be much more complicated than that, but I'm not sure about this. It's pretty complicated.
This construction can be implemented not only for GLM.
Yeah, sure. That's precisely what I was saying. You can do the same trick now here for arbitrary group.
I missed the right. Why is the right hand word needed in this system?
It is a way to interpret this operator without resorting to the coordinates. Because these Dij, they are sort of coordinates. It's coordinate way to write down.
Is it very long to explain this again?
Again, this is a coordinate-free way to explain it. There were several coordinate-free ways. The first one was with this co-multiplication, and here is the one which deals with differential operators. You take differential operators on matrices, regard them as differential operators on GLN group. It's a very appropriate way to regard them. Then you can use these generators of the Lie algebra of GLN to identify these polynomial differential operators with this tensor product. So this is equal to this, where this is left invariant part.
Is differential operators the same as universal enveloping algebra?
Left invariant operators are precisely universal enveloping algebra, and that's precisely this. So I identify the left invariant part of this decomposition with the universal enveloping algebra. Now I take arbitrary function on the group, polynomial function on the group. Take arbitrary element in the universal enveloping algebra. I interpret the function on the group as a degree 0 differential operator. I interpret this element in the universal enveloping algebra as an element in left invariant differential operator. I take the commutator as in the sense of differential operators. Then I use this identification again to write down the commutator as the sum of tensor products of certain elements from certain functions and certain elements of the universal enveloping algebra. After this, I just take the values of these functions at the point A in GLN. So I can assume that A is actually non-degenerate. So it is an element in GLN capital. So this is some operation which you get from, which takes elements from universal enveloping algebra and gives you other elements in the universal enveloping algebra. And I claim that if you take f, the function, to be equal just to the trace of matrices in GLN, then what you get will be precisely equal to this operator. And this gives you some hopes and some insight on how you can extend this construction from GLN case to the case of other Lie groups in the algebras in a very fairly coordinate-free way. In a fairly coordinate.
What would you get if you replaced f by trace of instead of trace of x squared?
Yeah, more or less. You do this. You do actually. I think the most appropriate way would do.
Extend it to semi-simple algebra. At least trace of x cannot be. The trace of x squared can be. Is the killing.
It's either this, or you can actually take other representations. You can take other representations of.
You could take the trace of. You could take the pairing of the killing form with some givens.
Yes. So you have lots of variants here. You can change this function in various ways. And now the fact that you take its values at a, it's more or less corresponds to the idea of shift, in my humble opinion, so to say. Now, let me say a few words about the proof of this fact. The proof is very technical and not very insightful, but I still feel obliged to speak a little bit about it. Proof is actually based on the fact that Mishenko-Fomenko algebras exist and are unique. Of the quantum Mishenko-Fomenko algebras. Actually, Rybnikov gave the following characterization of quantum Mishenko-Fomenko algebras. He showed that even before he had the construction of quantum Mishenko-Fomenko algebras in all situations, he gave the following characterization, that there exist certain set of elements explicitly expressed in terms of the root system of the corresponding Lie algebra. So you actually need to assume that your algebra is semi-simple. Yes, I assume that G is semi-simple. Elements in U, G, L, N. Well, second filtration, let's put it this way. F2. Filtration 2 means that you consider quadratic and linear elements, such that A hat Mishenko-Fomenko is equal to the centralizer of these elements. In case G is equal to GLN, this
this is G, UG, not UG. The top.
This is sorry, yeah, it's UG for you and arbitrary G.
And what is F2 again?
It's a second degree. That's the second filtration. It's the second filtration. That's the elements in universal enveloping algebra generated by no more than two, well, products of no more than two elements in G. So when we have G equal to GLN and A diagonal with distinct eigenvalues, diagonal simple with simple spectrum, then these elements which Rybnikov found are first I varies from 1 to n. So that's simple. You just take the diagonal elements. And 2, which is much more interesting, you take Ti of A to be equal to the sum Eij Ej for all j not equal to I divided by AI minus AJ. So the sum is taken over all j not equal to I, all j is not equal to I.
This is the definition of T.
These are the elements T, quadratic elements. So there are linear elements in F2 of GLN and quadratic elements. So these are linear elements. And these are quadratic elements. And the claim is.
Why isn't this is a tensor product?
Sorry?
This thing is a tensor product.
There is no tensor product. It's
It's
just.
in the universal envelopment.
Sorry?
It's in the universal
Yeah, it's just the product of elements in the universal envelopment. Yeah, just this. The claim is now the idea, the Rybnikov's theorem. Actually, if you pair the existence theorem due to Rybnikov and others, and this observation of Rybnikov, that if this quantum Minkov-Fomenko algebra exists, it should be centralizer of this space, we obtain the following simple result, that an element alpha.
Sorry, what's the statement about TIA?
Huh?
Sorry.
Uh-huh. So it exists if and only if. So an element alpha is an A hat MF if and only if A commutes with EII and A alpha commutes with TI of A for all i's. In particular, if alpha commutes with EII, alpha commutes with TI, and beta commutes with EII, and beta commutes with TIA, then alpha commutes with beta. A very simple observation, which follows directly from the existence of the Minkov-Fomenko algebra and from its characterization given by Rybnikov. Now it only remains to prove that if you take this operator D and apply it to this set, apply it to the center, the elements you obtain will belong to the centralizer.
So they do come in with EIA and they do come in with TI.
Yeah, that's the only thing you need to check. And you can do this by induction. And this is not very hard. But the most remarkable thing is that when you try to do similar things for non-GLN algebras, this fails. It fails. You don't get it. We need to do some other things to get the result in non-GLN case. However, when you apply these operators to the generators of the first type of the centers of universal enveloping algebras, UG, from classical series. If G is from classical series, A, B, C, or D, anything, and you take the analog of this operator and apply it not to any element in the center, but to some very special set of generators of the center of the universal enveloping algebra, you still get quantum Minkov-Fomenko. It's quite an interesting thing, I'd say.
So is Rybnikov's result only true for GLN or is it true for any?
It's true for anything. Rybnikov's result is true.
So this thing EII.
You can modify. You can have to modify it. Yeah, it should be called Cartan, and this will be expressible in terms of the roots, of root spaces and values of the roots on A.
So why can't you? What happens?
I don't remember it.
No, you said this thing.
It just doesn't work. I don't know. We do it by we apply the same construction. I believe that it's because we didn't do the correct thing to generalize D hat to other Lie algebras. You actually need not to do this, to use the powers of D.
But if you use that formula which was there, the one which it was without coordinates.
Yeah, I think the coordinate-free approach would.
It works.
For non-GLN case?
So it means that this is not a direct translation of that formula in the non-GLN case.
Yes, that's what I would say, that in a non-GLN case, you should use some other translation.
That formula is still correct.
Yes, I believe it should be. I should be It should be correct in coordinate-free case. Yeah. The coordinate-free formula should be correct. I think that's all because
Okay.
I'm quite exhausted after
Mhm.
my lectures.
Yeah, lectures today.
Can you give me a microphone?
Yeah, sure.
Well, thanks a lot. Questions, remarks? Nothing. No question, no remark.
Sorry, it's just so many interruptions last week, so I'm sorry.
Sorry?
I made so many interruptions, I had some
Yeah.
questions, I'm sorry.
Yeah.
I could do something
Okay.
in French. I'm sorry, that's even
No,
worse.
Okay.
That's even worse that I could disturb you from, I went
No,
outside
because
to not disturb
I
you.
didn't know you spoke French.
Well, better than Russian. This doesn't need to be.
Well, thanks a lot. We shall meet in 2 weeks.
Sorry.
No, it was Alex saying.
Goodbye.